In this video, we'll study human 2D pose estimation, the problem of localizing anatomical key points or parts that has largely focused on finding body parts of individuals. Inferring the pose of multiple people in images, especially socially engaged individuals, it presents a unique set of challenges. Each image may contain an unknown number of people that can occur at any position or scale. Second, interactions between people induce complex spatial interference due to contrast and contact, occlusion and limb articulations, making association of parts difficult. A common approach is to employ a person detector and perform single-person pose estimation for each detection. That's a top-down approach that directly leverages existing techniques for single-person pose estimation but suffers from early commitment. If the person detector fails, and it may do so when people are in close proximity, there is no recourse to recovery. Furthermore, the runtime of these top-down approaches is proportional to the number of people, because for each detection, a single-person pose estimator is run, and the more people there are, the greater the computational cost. Nevertheless, we will analyze several approaches of single-person pose estimation. The problem of human pose estimation can be formulated as the task of finding the position of human body key points, head, shoulders, elbows, wrists, and so on, and we can formulate this as a regression problem. Attempts exist to train a convolutional neural network to regress the location of the human joint positions, X and Y, using L2 laws. It may work well, but on a very specific dataset, such as a dataset of TV presenters. However, instead of regressing the joint positions directly, there were an idea to regress a heat map of the joint positions separately for each joint in the input image. At training time, the ground truth labels are heat maps synthesized for each joint separately by placing a Gaussian with fixed variance and centered at the joint position. This network can be fully convolutional, and the loss can be L2, which penalizes the squared pixel-wise differences between the produced heat map and the synthesized ground truth heat map. Of course, the approach is to regress the location of key points is naive for more complicated tasks. Before we proceed to the next part, it is worth noting that there is another formulation of the human pose estimation task. It is segmentation. You can see on the image that we predict the class for each pixel of the human body. We can use any segmentation method for solving this problem. All the above detectors work well to estimate the posture of one person. As we have said before, we can apply them after detecting people on image, but this top-down approach has some drawbacks. The most serious is that the inference time is proportional to the number of people. In contrast, bottom-up approaches are attractive, as they offer robustness to early commitment and have the potential to decouple runtime complexity from the number of people in the image. Yet, bottom-up approaches do not directly use global contextual cues from other body parts and other people. In practice, bottom-up methods do not retain the gains in efficiency, as the final parse requires costly global inference. The deep cut algorithm, a bottom-up approach that jointly labels part detection candidates and associates them to individual people, requires solving the integer linear programming problem over a fully connected graph, but that's an NP-hard problem, and the average processing time is on the order of hours. There was an attempt to build on deep cut with stronger part detectors based on residual networks and image-dependent pairwise scores. That vastly improved the runtime, but the method still takes several minutes per image, with a limit on the number of parse proposals. Now let's talk about the state-of-the-art and multiple pose estimation task that works in real time. The key point of this method is using part affinity fields. This method takes the entire image as the input for a two-branch CNN to jointly predict confidence maps for body part detection and part affinity fields for parts association or limbs. The parsing step performs a set of bipartite matchings to associate body part candidates that finally assembles into full body poses for all people in the image. The CNN that predicts feature maps for body parts and limbs is a multi-stage. Each stage in the first branch predicts confidence maps of body parts, and each stage in the second branch predicts PAFs of limbs. After each stage, the predictions from the two branches along with the image features are concatenated for the next stage for refinement. This process you can see in the left picture. Confidence maps of the right wrist in the first row and affinity field in the second row of right forearm across stages. Though there is confusion between left and right body parts and limbs and in early stages, the estimates are increasingly refined through global inference in later stages, as shown in the highlighted areas. Given a set of detected body parts, how do we assemble them to form the full body poses of an unknown number of people? We need a confidence measure on the association for each part of body part detections. That is, that they belong to the same person. In other words, we should predict not only the location but also the orientation information across the region of support of the limb. For this task, we could use part affinity fields. The part affinity field is a 2D vector field for each limb. For each pixel in the area belonging to a particular limb, a 2D vector encodes the direction that points from one part of the limb to the other. For instance, in the right picture, in the ground truth feature map, or part affinity field corresponding to the forearm, the value at the point P is the unit vector from J1 to J2, and K is the person ID in the image. For other points, the vector is zero valid. Having this key points candidates confidence map from our convolutional neural network and orientation of limbs, we could find the optimal association of key points to people by solving a maximum weight bipartite graph matching problem for graph where vertices are the key points candidates and edges are weighted limbs, as in the bottom left picture. The weights are the confidence of the association, and they can be calculated as the line integral over the corresponding affinity field along the line segment connecting the candidate part locations. To summarize, human pose estimation aims to predict locations of anatomical key points for individual people, and we can employ part-based methods for that, like those used for key point regression. Semantic segmentation machinery forms the natural basis for pose estimation, along with some other hacks like the affinity fields.